Hello friends, during our previous discussion we have been talking about the various aspects of BJTs. Now we will discuss the second major type of transistor, the FET, that is field effect transistor. FETs are unipolar devices because unlike BJTs that use both electron and hole current, they operate only with one type of charge carrier. The two main types of FETs are the junction field effect transistor and the metal oxide semiconductor field effect transistor. The term field effect relates to the depletion region formed in the channel of a FET as a result of voltage applied on one of its terminals called the gate. Recall that a BJT is a current controlled device, that is, the base current controls the amount of collector current. A FET is different. It is a voltage controlled device where the voltage between two of the terminals, that is gate and source, controls the current through the device. A major advantage of FETs is their very high input resistance. Because of their nonlinear characteristics, they are generally not as widely used in amplifiers as BJTs, except when very high input impedances are required. However, FETs are the preferred device in low voltage switching applications because they are generally faster than BJTs when turned on and off. The IGBT is generally used in high voltage switching applications. The JFET, the junction field effect transistor, is a type of FET that operates with reverse biased p-n junction to control current in a channel. Depending on their structure, JFETs fall into either of two categories, N channel or P channel. After completing this section, you should be able to discuss the JFET and how it differs from the BJT. Describe the basic structure of N channel and P channel JFETs and explain the basic operation of a JFET. Figure here shows the basic structure of an N channel junction field effect transistor. Wire leads are connected to each end of N channel, the drain is at the upper end and the source is at the lower end. Two p-type regions are diffused in the n-type material to form a channel and both p-type regions are connected to the gate lead. For simplicity, the gate lead is shown connected to only one of the p regions. A p-channel JFET is shown in part B of the figure. Basic operation. To illustrate the operation of a JFET, figure here shows DC bias voltages applied to an N-channel device. VDD provides a drain to source voltage and supplies current from drain to source. VGG sets the reverse bias voltage between the gate and the source. The JFET is always operated with the gate source p-n junction reverse biased. Reverse biasing of the gate source junction with a negative gate voltage produces a depletion region along the p-n junction which extends into the N channel and thus increases its resistance by restricting the channel width. The channel width and thus the channel resistance can be controlled by varying the gate voltage, thereby controlling the amount of drain current ID. Figure here illustrates this concept. The white areas represent the depletion region created by the reverse bias it is wider towards the drain end of the channel because the reverse bias voltage between the gate and the drain is greater than that between the gate and the source. Greater VGG narrows the channel between the white areas and increases the resistance of the channel and decreases ID, and on the other hand, less VGG widens the channel, which decreases the resistance of the channel and increases ID. We will be discussing JFET characteristic curves and some parameters later in this lecture. JFET symbols. The schematic symbols for both N channel and P channel JFETs are shown in figure here. Notice that the arrow on the gate points in for N channel and out for P channel. Drain characteristic curve. Consider the case when the gate to source voltage is 0. This is produced by shorting the gate to the source as shown in figure A, where both are grounded. As VDD is increased from 0 volt, ID will increase proportionally. This is shown in part B of the figure between point A and B. In this area, the channel resistance is essentially constant because the depletion region is not large enough to have significant effect. Because VDD and ID are related by Ohm's law, this is called the ohmic region. At point B in figure, the curve levels off and enters the active region where ID becomes essentially constant. As VDD increases from point B to point C, the reverse bias voltage from gate to drain produces a depletion region large enough to offset the increase in VDS, thus keeping ID relatively constant. For VGS is equal to 0 volts, the value of VDS at which ID becomes essentially constant, point B on the curve in figure is the pinch off voltage Vp. For a given JFET, Vp has a fixed value. As you can see, a continued increase in VDS above the pinch off voltage produces an almost constant drain current. This value of drain current is IDSS and is always specified on JFET data sheets. IDSS is the maximum drain current that a specific JFET can produce regardless of the external circuit, and it is always specified for the condition VGS is equal to 0 volts. Breakdown. As shown in the graph in figure, breakdown occurs at point C when ID begins to increase very rapidly with any further increase in VDS. Breakdown can result in irreversible damage to the device. So, JFETs are always operated below breakdown and within the active region, that is between point B and C on the graph. VGS controls ID. Let us connect a bias voltage VGS from gate to source as shown in part A of the figure here. As VGS is assigned increasingly more negative values by adjusting VGG, a family of drain characteristic curve is produced as shown in part B of figure. Notice that ID decreases as the magnitude of VGS is increased to larger negative values because of the narrowing of the channel. Also notice that for each increase in VGS, the JFET reaches pinch off, where constant current begins at values of VGS less than Vp. The term pinch off is not the same as pinch off voltage Vp. Therefore, the amount of drain current is controlled by VGS as illustrated in this figure. The value of VGS that makes ID approximately 0 is the cutoff voltage VGS off, as shown in part D of the figure. The JFET must be operated between VGS is equal to 0 volts and VGS off. For this range of gate to source voltage, ID will vary for a maximum of IDSS to a minimum of almost 0. As you have seen, for an n channel JFET, as VGS becomes more negative, ID gets smaller in the active region. When VGS has a sufficiently large negative value, ID is reduced to 0. As shown in the figure, this cutoff effect is caused by widening of the depletion region to a point where it completely closes the channel. Comparison of pinch off voltage and cutoff voltage. As you have seen, there is a difference between pinch off and cutoff voltages, but there is also a connection. The pinch off voltage Vp is the value of VDS at which the drain current becomes constant and equal to IDSS and is always measured at VGS is equal to 0 volts. However, pinch off occurs for VDS values less than Vp when VGS is non-zero. So, although Vp is a constant, the minimum value of VDS at which ID becomes constant varies with VGS. VGS off and Vp are always equal in magnitude, but opposite in sign. A data sheet usually will give either VGS off or Vp, but not both. However, when you know one, you have the other. For example, if VGS off is equal to minus 5 volts, then Vp is equal to 5 volts. JFET universal transfer characteristic. You have learned that a range of VGS values from 0 to VGS off controls the amount of drain current. For an n channel JFET, VGS off is negative, and for a p channel JFET, VGS off is positive. Because VGS controls ID, the relationship between these two quantities is very important. Figure here shows a general transfer characteristic curve that illustrates graphically the relationship between VGS and ID. This curve is also known as transconductance curve. Notice the bottom end of the curve is at a point on the VGS axis equal to VGS off, and the top end of the curve is at a point on the ID axis equal to IDSS. This curve shows that ID is equal to 0 when VGS is equal to VGS off. ID is equal to IDSS over 4 when VGS is equal to point VGS off. ID is equal to IDSS by 2 when VGS is equal to 0.3 VGS off and ID is equal to IDSS when VGS is equal to 0. The transfer characteristic curve can also be developed from the drain characteristic curves by plotting values of ID for the values of VGS taken from the family of drain curve at pinch off as illustrated in figure for a specific set of curves. Each point on the transfer characteristic curve corresponds to specific values of VGS and ID on the drain curves. For example, when VGS is equal to minus 2 volt, ID is equal to 4.32 milliamperes. Also, for this specific JFET, VGS off is equal to minus 5 volt and IDSS is equal to 12 milliamperes. A JFET transfer characteristic curve is expressed approximately as ID is approximately equal to IDSS into 1 minus VGS over VGS off whole square. With this equation, ID can be determined for any VGS if VGS off and IDSS are known. These quantities are usually available from the data sheet for a given JFET. JFET forward transconductance. The forward transconductance GM is the change in drain current for a given change in gate to source voltage with the drain to source voltage constant. It is expressed as a ratio and has the unit of Siemens and is given by this equation. Other common designations for this parameter are GFS and YFS, that is forward transfer admittance. GM is an important factor in determining the voltage gain of a FET amplifier. Because the transfer characteristic curve for a JFET is nonlinear, GM varies in value depending on the location on the curve as set by VGS. The value of GM is greater near the top of the curve than it is near the bottom as illustrated in the figure here. Input resistance and capacitance. As you know, a JFET operates with its gate source junction reverse biased, which makes the input resistance at the gate very high. This high input resistance is one advantage of the JFET over the BJT. Recall that a bipolar junction transistor operates with a forward biased base emitter junction. JFET data sheets often specify the input resistance by giving a value for the gate reverse current IGSS at a certain gate to source voltage. The input resistance can then be determined using the following equation: Rn is equal to VGS over IGSS, where the vertical lines indicate an absolute value. AC drain to source resistance. You learnt from the drain characteristic curve that above pinch off the drain current is relatively constant over a range of drain to source voltages. Therefore, a large change in VDS produces only a very small change in ID. The ratio of these changes is the AC drain to source resistance of the device and is given by this equation, where RDS is equal to change in VDS over change in ID. Data sheets often specify this parameter in terms of the output conductance GOS or output admittance YOS for VGS is equal to 0 volts. So friends, here we come to the end of our discussion and therefore we sum up. Field effect transistors are unipolar devices. The three FET terminals are source, drain and gate. The JFET operates with a reverse biased PN junction. The high input resistance of a JFET is due to the reverse biased gate source junction. Reverse bias of a JFET produces a depletion region within the channel, thus increasing channel resistance. For an N channel JFET, VGS can vary from 0 negatively to cutoff. For a P channel JFET, VGS can vary from 0 positively to VGS off. A FET is called a square law device because of the relationship of ID to the square of a term containing VGS. So, that is it for today. In the next lecture, we shall discuss the JFET biasing and the ohmic regions. Thank you very much.